All right, so this video is going to be on some leaving groups as well as some nucleophiles. So, um, the general reaction, right? We got our substrate here, also called our electrophile, or it contains our electrophilic carbon, and then we have a nucleophile, the product, and the leaving group, right? So, this is the interest of this particular section, that leaving group. Okay, so the better leaving group is the one that is the weaker base. Okay, so I told you time and time again, acid-base chemistry is really all organic chemistry is all about. It's Lewis acid-base chemistry, Bronsted-Lowry acid-base chemistry, and it's sterics, right? So hydroxide versus water. Water is the better leaving group because it's the weaker base. So this is a very obvious kind of explanation. Now, I want to, since I used water as an example, I want to kind of give you another notation. You can have an alkyl group with an LG that represents the leaving group instead of that X, because we call that X the alkyl halide, right? So here is another trend. Some gorgeous boxes for you. Basically, across a row, basicity decreases, and so that means that across a row, the leaving group ability increases. Okay, so as we go from like nitrogen to oxygen to fluorine, for example, or even below that. So if we had like phosphorus and sulfur. And then on the other hand, if we go down a group, basicity decreases as well. And so that means that the leaving group ability is going to increase. So going from fluoride to iodide. Okay. And remember, iodide is a weaker base because it is more polarizable. It's a larger atom. Distribution of that negative charge is more easily distributed. Okay. So all good leaving groups are weak bases. Look at the conjugate acids if you want to know what's up. Okay, so we're super awesome at that stuff, right? So looking at pKa's and whatnot. So let's go ahead and create a chart right quick. We got our starting substrate. We'll have a leaving group. That's also going to be our conjugate base in this case. We'll have an acid column and a pKa. So alkyl chloride, we get a chloride, and HCl is the acid. pK is -7. Bromine, bromide, HBr, -9. Iodide, HI, -10 for the pKa. And then we've got OH2 on there. That's leaving as water. H3O plus is the conjugate, or is the acid. So those are the pKa's of these particular leaving groups. As you can see, the increasing acidity goes from chlorine to bromine to iodine, and that is a decreasing conjugate basicity, which means that it's a better leaving group. And so that's kind of the explanation as to why, as we go down a group, we have an increase in leaving group ability. So let's look at some weak sauce leaving groups. We got a fluoride, an hydroxide. We'll have an amide, NH2. And then we have a hydride, H minus. And then we have just a carbide, so like the carbon with a negative charge on it. All these pKa's are really high. You can even see that fluoride, even though it's not terribly high, it's still somewhat acidic, is no good for a leaving group. They're all terrible, as my boy Charles Barkley would say. Old Chuck. All right, so let's take a look at an example. So now that we know a little bit more about leaving groups, we got this alkyl chloride plus water, and that ends up going after a proton transfer to an alcohol, right? And so, well, wait a second. We just said that water and chloride were both leaving groups, right? And so, what you talking about, Willis? So, yeah, that's totally okay because they're both nucleophiles as well, and they both have a lot of electrons. So, what you want to do is look at the basicity to determine which direction the reaction will go. So equilibrium always favors the products of nucleophilic substitution when the leaving group is a weaker base. Okay, so in this case, if in order for the reaction to move forward, the chloride would have to be a weaker base than the water. So how do we do that? Well, we got to look at that pKa's, right? So chloride, then HCl is the pK is -7, and then we have H3O plus is -1.7. Since -7 is a stronger acid, that means it has a weaker conjugate base, Cl minus, and therefore the reaction would proceed forward and all is good. And that's how you do it. Okay, so pKa's are coming back at you hard. Telling you, that's more acid base chemistry, and that's what it's all about in OChem. So get that practice. All right, so next thing we want to look at is nucleophilicity. Okay, so nucleophilicity, we kind of have seen what it does, right? We does some substitution reactions, but a nucleophile in general is just an electron-rich species, and it's also going to be considered a Lewis base. But what about a base? It's an electron-rich species, and then I'm specifically referring to like a Bronsted base, right? So what's the difference? Well, a nucleophile attacks an electrophile, while a base attacks a proton. So H plus, even though H plus is an electrophile technically, we kind of differentiate between an H plus electrophile and then all the others. Okay, that's going to give us the nucleophile versus base. So nucleophilicity versus basicity. So in general, a strong base is going to be a strong nucleophile, and that's usually exclamation point to the 5th power. Well, that was an exaggeration that didn't work out. Now, number one, there's 3 factors here. Stronger base is a stronger nucleophile when we are comparing the same atom. Okay, so what do I mean by that? Well, let's say we were comparing this acetate ion, that oxygen atom, to a hydroxide ion, which is still an oxygen atom. Well, since hydroxide is a stronger base because it doesn't have resonance, then it is also going to be the stronger nucleophile. So we're comparing oxygen to oxygen, and it's all good. So, factor number 2. Well, let's say that we have negatively charged nucleophiles. Those are always going to be stronger nucleophiles than their conjugate acids. Okay, so they might look like Nu with an H on it. Okay, and so again, hydroxide versus water. Okay, hydroxide. I'm going to put these lone pairs on here just to kind of give you an indication, because sometimes you can have a nucleophile with a hydrogen on it, right? Like water. So hydroxide would be better in that case. Number 3, as we go from right to left, on my right to left, across a row, nucleophilicity increases as the basicity increases. Okay, so we have CH3 minus, NH2 minus, OH minus, F minus. So as we go from right to left, we are increasing in basicity, and therefore we are also increasing in nucleophilicity. So fluorine is a very electronegative atom and loves to have that extra electrons, and so it's totally fine being negative. So by usually to the unexaggerated 5th power, I meant like nucleophilicity decreases with steric hindrance. So if we have like a really strong base, it doesn't matter. It's really strong base with a lot of steric hindrance, it's going to be a weak nucleophile. So got a strong base in ethoxide, got a strong base in tert butoxide, right? The pKa's are like 16 and 18 respectively, so for those acids. Strong nucleophile for ethoxide, but a weak, JK, we're not even going to call it weak, we're just going to call it non-nucleophilic, because it doesn't even act as a nucleophile. That's how much steric hindrance there is on this guy. And the reason is because you can have this situation because strong base just grabs a little itty bitty proton, right? Easy peasy, no problem, easy button, time and time again. Okay, but a nucleophile has to attack an sp3 hybridized carbon, right? And so there's going to be a lot of shoulder rubbing in this case, right? I'll give you a poor hypothetical scenario. Let's say we have this tributoxide attacking that carbon with the chlorine on it. There's just so much activity here. It's like, move, get out the way. If you see me on the highway, get the heck out of my way. Rated G version for ludicrous. So too much steric hindrance is just not going to happen. It's going to end up swooping on a proton somewhere, and that's it. Okay, so remember, tert butoxide is a strong base, weak, or a non-nucleophilic strong base. So now what we want to do is compare nucleophiles in nucleophilicity in different solvents. Okay, so since we have those polar bonds for those leaving groups, we got polar solvents required. So we have two types of polar solvents, and those are polar protic and polar aprotic solvents. Okay, so I went ahead and cheated and threw all those polar solvents down for you real quick. The ones on the left are polar protic because they have a proton, an acidic proton. The ones on the right are polar aprotic because they are polar because they have those heteroatoms, but they don't have that proton that can hydrogen bond. Okay, so look at all of the names, learn them, love them, like them, remember them, and what type of solvent they are. Okay, so this is really important for nucleophilic substitution reactions as well as elimination reactions, which are the next chapter. Okay, so the effects on nucleophilicity, or simmer down now. Effects on nucleophilicity. Okay, so what does the polar protic solvent have an effect on, or what effect does it have on the nucleophile? Well, polar protic solvents can hydrogen bond, so therefore they can solvate cations and box it up because it's really important, and anions. And they can do it really well. Okay, Jess, what are you talking about? What do you mean? How are they doing it? Well, cations basically solvate via ion dipole interactions because you have the like Na plus, for example, like sodium chloride. The Na interacts with the delta negative of another solvent molecule, and then the anions are solvated via hydrogen bonding, which is awesome, as you know. Okay, so the nucleophile, how does that affect the nucleophilicity? And so basically it increases down a column. Okay, so let me give you an example. Well, just the halogens, of course. So we've got fluoride, chloride, bromide, iodide as we go down, and then here's a lovely arrow for you. I just said that increases as you go down a column, right? And so that means iodide is a stronger nucleophile than fluoride, right? So increased nucleophilicity in polar protic solvents specifically. Okay, we got to remember this. Increased nucleophilicity in polar protic solvents due to the increase in size of the nucleophile, or the ion, okay, in this case. That's just iodide. It's just so big that it can't be solvated very well by the solvent, and it's still available to attack, right? So I like to think of iodide as a polarizable blob of electrons, and you can like squeeze under doors like little rodents and stuff. So squeeze under the door would be like an analogy for like through solvents to attack an electrophile. Okay, so of course remember this is opposite basicity. Okay, so that's what's tricky about this polar protic solvent. It's opposite basicity. Okay, now let's take a look at these polar aprotic solvents and their effects on nucleophilicity. Ellipsis. ... So there's no hydrogen bonding with these particular solvents. Okay, and that means there's only going to be the dipole-dipole interactions. Well, remember that time when I said that the ion-dipole interaction was solvating cations, and the anions are solvated via hydrogen bonding? Well, that's the thing. So polar aprotic solvents solvate only cations well. And that's because they only have that dipole-dipole interaction. So what does that mean for old iodide or old fluoride or bromide? Well, that means that solvation. Sorry, let me write that. I'm gonna write it on top. So solvation of the bromide ion is bad, while solvation of the sodium cation is good. All right, and so here is acetone as an example. That oxygen is delta negative because it is a more electronegative than carbon. So that delta negative is interacting with the sodium cation. It's got the lone pairs on there too. They could just kind of grab onto that, and you surround that sodium cation, right? But bromide ion and acetone, they don't really want to interact. They're kind of like snobby, and they don't want to hang out. So bromide is viewed as what's called a naked ion because it's literally just a low-key kind of floating around as an ion, right? And so nucleophilicity parallels basicity in this case. So let me make sure that we emphasize this. Sorry, I want to emphasize that this is also in polar aprotic solvents. Okay, so nucleophilicity parallels basicity in polar aprotic solvents. Okay, polar aprotic solvents, exclamation point, asterisk, to the 27th power, whatever you got to do. Remember that, okay? It's opposite basicity in polar protic, and it's parallels basicity in polar aprotic. Okay, so let me draw this little chart real quick. We got the fluoride down to iodide, and we got the arrow going up this time, and we have an increase in basicity. Okay, and then that's also going to give us an increase in nucleophilicity. Okay, super important. Remember it, love it. Get that practice in. All right, bye.